Thank you very much for coming. Thank you very much for coming to this second lecture. Today, I'd like to talk about holography for conformal field theory with boundaries. Such a CFT with boundaries called BCFT, boundary conformal field theory. And we'd like to discuss holography for this BCFT. That also related to many interesting topics, including black hole information and also some non-trivial quantum entanglement physics and so on. Okay, so let me start. So, to construct gravity dual, holographic dual of this CFT with boundary, the crucial object is called end of the world plane. So let me explain this. This is a heuristic picture. We have a gravity. This green region is 3D. You can think this is like a gravitational space-time like our world. This green region is a gravity, but we place some wall, end of the world plane. So end of the world is really end, so there's nothing outside. Only this side, there is a universe. So if we send a gravitational wave, it's completely reflected back. But also this is a brane, so if we send some gravitational waves, then this brane also vibrates. So there is a non-trivial degree of freedom localized on this end of the world. So this end of the world brane plays crucial roles in holography these days, and it's sort of, if you run string theory, D branes plays a very important role. And in the same way, if we think about the area CFT of holography, end of the boundary plays some role, some important role like D branes. It is it is more than just a boundary actually. That's why I would like to explain this talk. So if we think this holographic dual of this gravity, so this maybe sort of anti-Doshita space, and there is some end of the world brane, then its dual theory lives on this real boundary. So this is an extra dimension, and there's a Z direction, which I gave a talk in this last Monday. So this is a boundary, and this degree of freedom is localized on the boundary. This is a holography, but also there is a boundary of boundary here. Intersection between end of the world brane, we call it EOW brane, end of the world brane, and also this usual ADS boundary, the intersection. This is a very important role, plays a very important role, and this is the boundary of this dual conformal field theory. CFT lives here. So CFT, so maybe let me write it. CFT lives here, and ADS spacetime is this green region. And this is the end of the world brane, and there is a boundary here. Boundary of CFT, and where this boundary, which is called BCFT, boundary conformal field theory, your freedom is localized here. Okay, so this is a framework we're going to work with. So the example of application of this end of the world, right? And there are many examples. There are more, more examples, but first of all, it plays a role of quantum system just with boundary. This is obvious. Let's take this time direction. There is a boundary, and space direction is like this semi-infinite. And to describe such a situation, we can use this, end of the world brane holography. And also recently, this is also applied to a very interesting problem, a black hole information problem. So we have an anti-Doshita space, and there is a localized mode actually, localized on this end of the world brane. So here, end of the world brane is situated at the ADS boundary, but it can vibrate. We assume actually different boundary condition, namely Neumann boundary condition, so that end of the world brane is dynamical. Then there is a localized gravity mode appears. And that means dual theory. So this ADS spacetime is dual to some conformal field theory coupled to some gravity. So it's a dual to some quantum gravity. This is a famous Landau-Sandram brane world setup. But then we can discuss some gravitational physics, quantum gravity physics, and using classical gravity dual. And that actually gives a nice understanding of black hole information problem. I will explain this also quickly later. And finally, this application to condensed matter physics or statistical mechanics, you can revert, you can take a weak rotation of this setup. So now time is this direction, this is space direction. So this is a space-like boundary. And but let's assume this is a Euclidean time region. So this is actually something called boundary state, and this is kind of state without almost no entanglement at all. It's like almost direct product state. But under Lorentzian time evolution, it's chaotic evolution. So entanglement generated each time. And we have some kind of chaotic evolution, and the entanglement entropy. Entanglement entropy is growing, and that actually describes thermalization, thermal behavior, no equilibrium dynamics. So in the end, we have a thermodynamical setup. So this is a no application to no equilibrium dynamics. Okay, and this talk is mainly based on this work. I'm going to actually talk about something called G-theorem, derivation of G-theorem from basic inequality in a quantum information theory, but this has also nice interpretation from the viewpoint of this holography with the end of the world plane, like this. And they also will mention some other cross-related works by us also. So the first work with Jonathan Harper is our postdoc, and Hiroki Kanda, who is our graduate student. And this third work is about the application of this holography with the end of the world brain to the setup with something called entanglement phase transition, and that I will explain. Some recently discussed by many condensed matter literature. And this is a work based on the work with Hiroki Kanda and Taishi Kawamoto and Masahide Sato, Yuki Suzuki, and Kenya Suzuki. They are all graduate students, and this way he's a postdoc in Harvard. Okay, so the content of my talk, I just finished the introduction. I just gave a heuristic picture of the end of the world brain. Now I give some precise prescription of ADS BCFT duality, and then go to this first main part, like Entropic G-theorem. G-theorem is a kind of monotonicity in quantum field theory in the presence of boundary. I will explain that. And it has a nice holographic derivation also. And that actually related to this theorem actually prohibits like wormhole configuration. So there are originally it's a very quantum field theoretical property actually in the light of ADS CFT holography, it actually constrains the topology of universe. That I will explain. And finally, I'd like to also talk about this other works, and its application to ADS BCFT to some entanglement-based transition by considering some scalar fields on end of the world. Okay, so anyway, if you have questions anytime, please ask. But maybe after 1 hour, so we'll have some break, short break. Okay, so let me talk about the ADS BCFT. So this means, we know, I explained ADS CFT in the first lecture. So B is a boundary. So here is a heuristic picture. So BCFT is like this. BCFT means some conformal field theory lives on the space with boundary. Like this M is a conformal field theory. M is a space-time where conformal field theory lives. So this has a boundary. So M and the boundary is a partial M, del M. This is a boundary. And let's take this a D-dimension. D-dimensional. So totally we call it a D-dimensional BCFT. Like this bulk region and the boundary region. But this is no gravity at all. This is just CFT. But with non-trivial things, we have a boundary. So what's the gravity dual of that? This is a question of ADS BCFT. Usually ADS CFT, as I explained, so boundary is just a just compact manifold, right? It's a sphere or just plane. Plane you can compactify by adding infinity. So then there are no boundary at all at the ADS boundary. So this theory, conformal field theory lives on this flat space RD, and this is equivalent to gravity in higher dimension because of holography, D plus 1 dimensional gravity on anti-Toshita space. This is ADS CFT correspondence. But what about this case, like BCFT? CFT lives on the manifold with boundary M. So the answer I will explain, but this here is just a very intuitive picture. So we just idea to construct gravity dual to extend this boundary towards the bulk. So this originally there is an anti-Toshita space here, like this. So we have a CFT here, and anti-Toshita space is equivalent to gravity. But we restrict region to this region, M. Then actually space, ADS space time also restricted to this region. Region surrounded by a red curve, red surface. This surface is exactly end of the world brain because space-time universe end at this point. There's nothing here. This white region don't have any at all. No gravity, no degree of freedom. And this inside this end of the world brain is called M. So it's BCFT, D-dimensional BCFT on M is equivalent to D plus 1 dimensional gravity with end of the world brain. That means region M. region N. This is a claim of ADS BCFT, and I want to give more details later. So, but anyway, important point how to specify this red surface end of the environment. This is a very important point. So for that, we take a gravity action. So we have some bulk term, this Einstein-Hilbert action, and with some matter Lagrangian. This here, N, right? This N. And there is actually boundary term which localizes this boundary. This is a Gibbons-Hawking term. This is usually, this is quite usual as you learn in the textbook. But also there can be some localized matter on this boundary. Sorry, what I'm sorry, I said something, sorry. So this integral is a whole Q, that means end of the world, right? So bulk region is this region N, and boundary, there is a two boundary, M and Q, right? Boundary of N is M and Q. And for M, we just put some Gibbons-Hawking term. I didn't write it, but actually there is a such term. So this is trivial, so usually in ADS-CFT. So I didn't write it, but there is a N square root minus H K. There is a usual Gibbons-Hawking term. This is not important. And the important thing is there is a boundary term for end of the world, Q. So this is this term. And not only Gibbons-Hawking term, there is a matter degree of freedom, so you can put some matter here. So this is actually plays very important role, some part of my talk. So we can put some matter here. Some matter degree. So this is this Lagrangian action. And yeah, H is the induced metric on this Q. And the X is a coordinate. And then, so this is a kind of, I mean, we have sub-region. So very geometrically important quantity is the extrinsic curvature defined by normal vector, derivative of normal. N is a normal vector. N is this, again, let me write it here. N is this normal vector, unit to normal vector. Anyway. And taking the covariant derivative of this guy, this defines this extrinsic curvature. This is a very important quantity to characterize the shape of this end of the world, right? For example, if we take Gaussian normal coordinates, always we can locally write the metric in this way, then extrinsic curvature means just derivative. So and it means surface is fixed by rho equal constant, then extrinsic curvature is just derivative of this metric by rho. Anyway, so the important point is that we take a variation. So to fix the boundary condition, we usually take a boundary as a variation, del I, and that gives, this is a famous formula, but this is a Gibbons-Hawking formula. Because Hawking term gives this term. But there is an extra contribution because we have this matter Lagrangian. So matter gives some energy stress tensor localized at the end of the world, right? So this is this T here. And we want to set this is 0, right? And variation principle makes sense. This should be, does vanish at the boundary. So that means there are two possibilities, delta H equals 0. This is the usual Dirichlet boundary condition. This is a usual ADS-CFT argument. Usual ADS boundary where metric is fixed, this is a Dirichlet boundary condition. But we don't want to do this because we want to keep, as mentioned, so Q is a very dynamical, vibrating branes. Then we use the other boundary condition, namely this term. First term is 0. This is Neumann boundary condition. So K is the extrinsic curvature. This is just the usual term when we take a variation of the metric. And this is the extra contribution from the matter fields localized on the brane. This is a boundary energy stress tensor. So this is much like, this is a kind of boundary version of Einstein equation. This equation plays a very important role in ADS-BCFT correspondence. But yeah, the reason why we choose Neumann boundary condition because we want to keep boundary dynamical and we don't want to fix metric on Q, right? So we want to fix metric M, right? This is a fixed, the CFT lives on, BCFT lives on M, and there are no gravity at all here. So this is a Dirichlet boundary condition. But in the bulk, we have a gravity, so we want to keep this dynamical. So that's the reason we take this boundary condition. But also, if you are interested in string theory, there is one clear way to realize this is namely orient fold. So orient fold is can be introduced at the end of the world plane of the space-time in string theory, and that actually requires basically K is 0, KB is 0, and TQ is 0, not TQ. If we can put some brane also on top of orange world, you can generate also TQ. So anyway, this is how we impose this boundary condition here. This boundary condition of Q is given by normal boundary condition. Okay. So yeah, this is just summary. So I already mentioned. So this BCFT lives on this manifold M with a boundary M is equivalent to gravity on asymptotically ADS spacetime which lives on N. Boundary of N consists of M union Q. And here this boundary we impose Neumann boundary condition. So this is a final claim of this ADS BCFT construction. Okay. If you have any question, please just ask me. Okay, but I didn't explain so much about BCFT. So more precisely, BCFT is defined the following way. So yeah, anyway, we have a boundary and there is a CFT. So CFT with boundary, but strictly speaking, most strict definition of BCFT is we require some conformal symmetry. So for specific boundary condition, a part of conformal symmetry are preserved. This is called boundary conformal field theory. So if we think D-dimensional conformal field theory, it has a SO2, D symmetry. But if we have a boundary, actually, so it leads to one dimension lower, right? It's one dimension lower theory. It can have a conformal symmetry SO2, D minus 1. So at the boundary, even if we introduce a boundary, still we can keep this symmetry. But the whole symmetry is broken, right? SO2, D is broken, but we can keep this partial subgroup of that symmetry. So this group of symmetry, this symmetry is preserved. We call, strictly speaking, this is called BCFT. So, and in other words, at the boundary, we impose this reflective constraint. T is the left moving mode and right moving energy. This energy stress tensor of left move, right move is difference is 0 at the boundary. This is actually gives this symmetry. And also, if we take a weak rotation, as I mentioned in the beginning, then this is time and this is space. Then this defines quantum states, and this quantum state is called boundary state or Cardi states. And that's satisfied in terms of Virasoro language. It's satisfied. This also preserved. This means that this state preserves SO2, D symmetry. In D equal to, I'm talking two-dimensional. This is a two-dimensional CFT language. This is a quite general language. But SO2, so originally SO2, 2, symmetry is there. There are two SL2R symmetry, but only one linear combination of SL2R symmetry is preserved in the presence of boundary. But however, this is a strict definition of BCFT. But when I talk about the ADS BCFT, actually we can in general we can take this TQ to be arbitrary. As long as it satisfies positive energy condition, like null energy condition. In that case, actually, in general, it breaks this symmetry. So still, roughly I'm calling that's also BCFT because it's just some CFT with bound. But there is a very nice class among them, and that preserve conformal symmetry. That is more mathematical or more standard language. It's called BCFT. So please just be careful about it. So, but yeah, the strict BCFT corresponds to only one. So the TQ, in general, if we put some the energy stress tensor here, it breaks boundary conformal symmetry. But if we choose TQ energy stress tensor proportional to induced symmetric with some coefficient, only in this case it really preserves this boundary conformal symmetry. It's easy to see from the symmetry argument. But also, this means that we have this equation, right? And T is also called tension of the brane. So it's a kind of tension of the brane. And yeah, okay. So for this case, we can easily solve the problem. So for this Poincare metric in any dimension, even higher dimension. So usually ADS-CFT is like this, right? This is a Z direction, and Z corruption, this is a UV cutoff. This upper half plane is a ADS spacetime. But we can cut out also some wedge by putting end of the Waldman. This is a Q, right? This is the end of the Waldman is Q. and we remove this region. So white region, there are nothing, no universe at all. This green region is our universe. This green region, gravity on this green region is equivalent to conformal boundary conformal field theory, which lives on M. Right? There are no the other side. Boundary conformal field theory lives on upper half plane, or maybe left half plane. So, and actually, we can easily solve this equation, and that gives, I mean, it's a kind of just a plane, just with some angle, always solve this equation, but with different values. So this gradient is related to tension. Now, if tension is zero, it's really vertical, like here. The tension can be negative, it go this way. It's cut out many. So tension is proportional to degree of freedom. So small tension means very small universe. But if zero tension is like meter, and large tension actually goes to this way. It almost covers everything. T goes to T can be go to 1. This largest value of T is 1. Then it's really go for this whole region almost covered. T minus 1 is like this. It's a very small region. Yes, okay. There is a question. So now let me answer the question. What's the difference between ADS BCFT and the usual entanglement wedge? A good question. But actually, this is completely different. So maybe I didn't prepare the slides. Okay. So yeah, picture looks similar. It is true, but the dimension is different. So in ADS CFT, let's take ADS. Okay. ADS D plus 1. Sorry, in my Monday's lecture, I set D plus 2, but I just let's stick to the D plus 1. This is more normal convention. Then this in this entanglement entropy calculation, gamma A is codimension to that with D minus 1 dimension. Okay, always minus 2 dimension. Black hole horizon also, like if you have 4-dimensional series, 2-dimensional sphere in the horizon, that is always codimension 2. Codimension 2. This is the 2. When we talk about entropy, always codimension 2. But here it's actually codimension 1. M is defined. This is a D dimension, right? And this Q is also D dimension. So dimension is different. That's the one basic difference. Another difference is minimal surface. We impose a minimal surface for entanglement, right? Minimal or extreme, minimum or extreme. That means actually K place of KAB, KK, KAA is 0. This is a minimal surface equation. It's different from this way. Right? This case, all components of AB, there is a constraint. But here it's only trace part is 0. Trace part of excessive curvature is 0. This is equivalent to extremal surface. This is an entanglement case. But in the ADS BCFT, you have to compute all components, and this is an over constraint equation. This is an over constraint. So one may wonder the problem. But here, even if you fix any ADS metric, some distorted ADS space-time, you can always find minimal surface because we just need to solve this. But if we have some given non-trivial ADS space-time, try to find this solution. There is try to find this solution. It's not guaranteed to give a solution. So that means, but actually there is a brane, so brane back reacts. So there is no solution, but that means brane can back react and change the geometry, change the metric, and so that this brane satisfies this equation. This is a situation in ADS BCF. This is very important, so I explain detail. Okay, so this boundary state looks like it satisfies level matching condition in string theory. Is it true? But this is yeah, okay, that's right. Yeah, of course, level matching condition. Level matching condition is L0 minus L0 bar equals 0. So that's yeah, of course part of that. Yeah, this is left-right symmetry, but there are no relation, no such a relation. But the boundary state is actually you can regard it as a D-branes. D-branes are boundary where open string ends, right? And that means really boundary of a world sheet. So boundary state is correspond to D-brane. This is a connection to string theory. Okay, I'm sorry, but okay, let's see. Okay. So this is another question is that why this this kind of situations preserve boundary free BCFT symmetry. BCFT. So why is that? Yeah, this is actually, so for example, this solution shows. This solution means that we have a boundary just upper half plane. Right? And that case is conformal symmetry is all preserved. And you can do some conformal mapping. So this is, you can do some conformal mapping. And then you can see from this setup, you can realize all setups which preserve conformal symmetry. But if you choose very complicated, boundary, so it breaks conformal symmetry. So that's way we can basically understand that. Okay, and the other question, as BCFT on the manifold M is dual to gravity asymptotically, but when your W is dynamic, not change the BC. Yeah. So okay, the point was, so anyway, if you send some gravitational waves, then this vibrates, right? Surface Q becomes dynamical. And that means that, so from the viewpoint of, boundary conformal field theory, we cannot send the signal from here, right? Inside, right? Because there are no universe outside. So this means that you excite some BCFT in the bulk, and that gives some effect at the boundary. So degree of freedom is Q is equivalent to this boundary degree of freedom of M. So if we excite the bulk of the region M, CFT, it affects the boundary dynamics. That's the thing. Okay. If you would like to receive further, okay. This boundary state looks like, okay. Yeah, I think this probably answer this question. Okay, let me go. So yeah, then this kind of idea also leads to another interesting connection. This is recently heavily used. This is called double holography. But actually, this means that 3 different setup is equivalent. First of all, as we claim, this boundary conformal field theory, as a CFT with boundary is equivalent to this setup of ADS BCF. It's an ADS BCF, yeah. But if we look this closely, there is the end of the world plane. As I mentioned, actually, you can show that there is a localized gravity mode localized here on Q. So there is a gravity, of course, bulk gravity, but there is some other gravity mode which really localized at the boundary. So if we think that way, so this green region is dual to BCFT, but another idea, green region is dual to this M and Q. M is a conformal field theory which couples to this gravity on Q, because this red guy, this localized gravity is lower dimensional. D-dimensional gravity lives on Q. So it's like gravity on Q coupled to CFT. This is a third picture. This connection is called brane-word holography. But one may ask, like, is these 2 connections consistent? Indeed, these 2 guys are equivalent because this gravity lives on lower dimensional ADS. It's like actually lives on ADS-D. So you can use ADS-D, roughly speaking, you can use ADS-D plus CFT D minus 1 to relate this to. This is actually D plus 1, right? The BCFT is on D. So that way, it's consistent with each other. So this is called double holography. This is very important also to understand black hole information thing, because we can talk about this gravitational holographic for gravity. And usually, holography is like between ADS-FT is between CFT and bulk gravity. But in this case, this gravity quantum, this is actually supposed to be quantum gravity because conformal field theory is also quantum. This quantum gravity is equivalent to the higher dimensional classical gravity. So this is another type of gravity and another type of holography we can deal with quantum gravity. Okay, so another application of this double holography is wedge holography. You can imagine this kind of double end of the word plane setup. This is usually BCFT, but with end of the word, double end of the word plane. So the claim is that this ADS spacetime green region is equivalent to gravity M coupled to gravity on Q1, Q2, but that's also equivalent to CFT lives on M, right? This is CFT lives on M. But you can assume this, two end of the ladder line squeeze to, so that it intersects along the line like this way. So you can squeeze this with us. Then it's actually this wedge region. This is though it looks like ADS, but this wedge region, gravity on this wedge region is equivalent to in the end this CFT gives of sigma. It's 2-dimension lower. But actually, usually holography relates 1 dimension lower, but in this setup, it can relate to d minus 1 dimension. And in the middle, there is a brane world, like hologram. So this gives some codimension to hologram. Okay, so now I go back to this holographic entanglement. So what we would like to do, calculate entanglement entropy in this ADS BCFT correspondence. So here is this is already I explained in the first lecture last Monday. So to calculate entanglement entropy, we decompose Hilbert space A and B. This is CFT lives here. I'm talking about time slice t equals 0. And we extend the boundary of A towards the bulk, and that so that this area becomes minimum. So it's like minimum area formula. So you can just choose gamma A so that area is minimized. And for time-dependent case, we can slightly relax the condition so that we don't require minimization, but we require just extrematization. Area function is stationary. And if there is a several discrete number of solutions, we just pick up minimum one. So this is a covariant prescription. So we're gonna apply this our setup. Probably mostly I can just apply this static form. But yeah, okay, so here is actually related to the previous question. And it's a different ADS BCFT and the entanglement wedge is different. So the entanglement wedge case, we have, as I mentioned, it's stress part of extreme curvature is 0, but ADS BCFT, we need to fix all components of KB, and also dimension is different, as I mentioned. Okay. And but yeah, this and then go to this and how we can generalize this holographic entanglement entropy in the presence of end of the world frame. So this is a very important point. So here is the answer to that question. So how we can calculate entanglement entropy for BCFT? So to define BCFT entanglement, this is a BCFT, right? So this is a CFT lives on the left half plane, and there's a boundary here. And we can pick up sub-region A anywhere you like, but let's take this purple region. And let's calculate entanglement entropy for A. This, of course, we can compute in principle in just field theoretical calculation by just taking a reduced tensor matrix and roll or replica calculation. But in terms of holography, if we take a holography, we use ADS BCFT. So this region M is dual CFT lives on M is equivalent to gravity lives on this wedge region, ADS D+1, but it's cut by end of the bottom by Q. And then calculation of entanglement entropy A, naively, if we just adopt the previous one, this one, then what we do just to do some calculation A, you can extend this A underway to the bulk and just calculate minimum area surface. But this is also okay. This is one possibility, but there is other possibility that it can end on the end of the world line, like some region. So we can end any region, but let's take B somehow. We fix some particular shape of B, but you can also end here. If you like B, you can also think about this kind of. There are infinitely many different possibilities. Anyway, once you choose that, then you just calculate area, right? Calculate area. This is the area of gamma A. But the point is that not only we minimize about gamma A, but also you can change this location B, right? Or shape of the size of B. And you have to take a minimization over that. And then you get a correct one. And indeed, in this case, actually, if you go this way, it's like get us rather than going to this connected one. This is called disconnected one. This is a connected one somehow. This gives actually this disconnected one gives a smaller entropy, so that it is a favor. I will explain more explicit example later. But in general, it can end of the world. So this is actually related to homology constraint. So usually we think this homology, so holographic entanglement, I didn't explain so much, but this gamma A and A should be homologous. It's a topological condition, homologous. And but here, non-trivial thing, we think Q is a trivial as a homology. So of course, in mathematical, Q is not trivial, but in physics, Q, because we impose Neumann boundary condition, as I mentioned, it's a Dirichlet boundary condition. Dirichlet boundary is not trivial, but any region which we impose Neumann boundary condition should be regarded as trivial. It's not, in other words, this part is a non-trivial Hilbert space, but this part is no longer independent Hilbert space. This is very important also to understand black hole information parts. But anyway, yeah, so this is a prescription. And in other words, what the B means in maybe one might think like what the B means in this CFT language, it's actually mirror. You know mirror method. Like to calculate a one-point function, for example, with a theory with a boundary, you usually put some mirror and compute two-point function, right? And then take a square root. You compute two-point function and take a square root. So this is exactly basically the same thing. So B is a kind of mirror of this region. And anyway, so one more thing, it's not in our in current context, which I also explained a little bit in last Monday. That is actually in the context of black hole information products, there is a nice formula, very important formula called island formula. And in that interpretation, actually, B is island. You can think B. So why did they are related? So actually, it's come from double holography. So in island formula, we talk about exactly the same setup like this. The same setup. So we take subsystem A. And here is a black hole. Black hole is here, and it radiates. There is a Hawking radiation, and Hawking radiation is captured by this observer who sits in region A. In the end, there's a penetration. So in the end, it goes here. So in that case, we want to compute the entanglement entropy for this region. This region is A. To calculate the region of A, then actually not only calculate just naive quantum field theory entanglement, we have to take this island formula. That means minimum of, so we create some island inside the black hole. The island. So we create area island and we compute island area, boundary of epsilon, as a boundary of sigma, plus some bulk entanglement. This is a normal quantum field theory entanglement, but not only A, but union sigma. So this is the island formula. And this island formula naturally appears here. That's the point. So this island formula I write it, okay? This island formula, so this is still not correct. We need a boundary of A, right? So, and the setup is again written like it. So the sigma is here, this is island, A is here. And this is the gravity, and this is the CFT. Okay, so this part is gravitating, but the other this part is not. This is CFT. And that case, to calculate entanglement for this region, we need this surprising formula. So there is some island region pops up, but this calculation already pops up because we just wanted to calculate this entropy for region A. But there is an end of the world line, so using this, this picture. So this brane world picture. So it looks like not only A but also Q. There is a gravity located here. So this is really dual theory looks like gravity coupled to CFT, right? Gravity is a gravity coupled to CFT. And we calculate the entanglement entropy for region A or CFT, but there is actually contribution from island. This is B is island. And so roughly speaking, and this term, area term basically contribution nearby this region B. And the other part is really connected part, right? This is sigma. So in other words, in this language is just sigma. So this connected part gives the second term. This is a bit heuristic explanation, but this actually indeed works very well. So already in the ADS BCFT, you see this island region. Okay. So you can see the explicit calculation here. So this is the ADS3 calculation, but maybe there is a question if this specific calculation entanglement entropy. Yeah, yes. I think the question. Sorry, I passed, but I talk about these three different double setup of double holography. You can compare entanglement entropy, and they all match. Yes, that is true. So yeah, but this is a hint of that argument. So holographic entanglement in the simplest setup, ADS3 BCFT2. So this is ADS3 is here. Okay. So ADS3 is here. ADS3 is here. And the BCFT lives here. And end of the variable is here. So we take, let's take this time direction and this space direction, semi-infinite space. And subsystem A is like this time and the band, and this is space, and region is A taken from this band, right? And it's length L, large L, capital L. And then this is subsystem A, and how we can calculate holographic entanglement, you can put some island region, B. So in this context, this is actually B region. This is a B. So we calculate this. Gamma A is this arc, is a gamma A. Okay. So you can end, gamma A can end of the end at the end of the vertical. This is the rule. So you can just pick up this length, and it's very easy to calculate. You get this result. And that means you have some half, if we completely go back to the boundary, there is a 3 over 3, C over 3 log epsilon divergence, but it's only half, right? So it's like 3 over 6 logarithmic divergence plus, depending on this angle is given by tension, actually. Tension determines angle. Angle means I'm talking this angle. This angle is related to tension, which gives this extra contribution. T equal 1 is really Q goes to infinity, right? It's a maximally large, right? T goes to 1, it's divergent. It's part of divergent. But T is equal to 1, equal to 0, it's really vertical. Right? Just compute this length, it should be 0, right? If 0, this part is 0. Because this term is already compute this length. So anyway, this is a formula. And so this is related to my next main part, actually. So this is, anyway, so this looks like there is a conventional logarithmic divergence, but plus some constant. So this constant depends on tension, right? It really depends on the boundary condition. So tension is determined by boundary condition. Boundary condition at this point. So in a generic theory, holographic theory, it's a lot of primary fields. And then there is a one-to-one correspondence between primary fields, primary state, and also one boundary condition, conformal boundary condition. This is called Cardi state, Cardi condition. And then, so you get in the large central charge limit, we get infinitely many different boundary conditions, and each boundary condition have a different value of tension. So tension T is a really deep, specifies boundary condition. This is a rough picture. And depending on the value of T, so we get a different value of constant contribution to entropy. And anyway, this is entropy. It looks like degree of freedom. So this is called boundary entropy. This is a very important quantity. It's called G function or boundary entropy. So this is a quantity I want to work with in the next section. If there is a question. And so, however, in your result of entanglement obtained by iron that evaluated are not equal unless tension is infinite. To make me no. Actually, unless tension is infinite. Tension is infinite, like we get this one, right? No. I think we discussed this case in my paper with Suzuki. You can look at my paper with Suzuki. That case, we can have a nice matching between these pictures. And in the case of large tension, so we can apply usual holography here. That case, more reliable calculation we can do. But even if we fix some particular angle, so you still get some nice matching. Okay, so now I go to this something called G-theorem. This is a theorem about this boundary entropy. So let me start with, but before that, I want to explain C-theorem. So G-theorem is a kind of boundary version of something called, very famous theorem called C-theorem. So let me first talk about C-theorem. So entanglement entropy, as we mentioned, is a nice measure of degree of freedoms in quantum mechanics, in quantum manual system. In two-dimensional quantum field theory, we get this logarithmic behavior. C is the central charge C over 3 log of length over epsilon. This is a very famous formula. And this central charge appeared here. And about central charge, there is a very famous theorem is known in 2D quantum field theory. This is called C-theorem. This is first proven by Zamochko. This argues that central charge C monotonically decreases under RG flow, renormalization group flow. If we go to high energy to low energy, for low energy observer, right, I cannot see so much, right? Cannot see so much high energetic excitation. So degree of freedom looks like small for low energy observer. This is quite natural, but to prove this is highly non-trivial. We need some relativistic invariance and unitarity, and then you can really show the central charge degree of freedom is decreasing under RG flow energy scale. And actually, indeed, so this is true for relativistic theory, but not necessarily true for non-relativistic theory. So this claim is intuitively true, but actually proof is highly non-trivial. And once this is proven, we can use this to follow RG flow. So if there is some very complicated theory, which we know UV theory, but we don't know infrared theory. But if we can calculate central charge in both theory, we can compare that, and we can talk about which one is correct, infrared limit and so on. So this C-theorem is very rigid and very useful theory. And so quantum information, but the important point is that this is of course proven in quantum field theoretical way, a field theoretic way, but there is another proof can be provided by using entropy, entanglement entropy. That's actually much easier somehow, very intuitively understand. So that clarifies the meaning of C-theorem from quantum information theoretical language. And this is first done by this Cassini and Fecha, 2004. So let me review also this proof. This is very simple and very intuitive and very geometric. So it's very instructive. So, but to prove that, we need, of course, a starting point. So how we can prove non-trivial theorem? There is a very famous and very fundamental inequality known in quantum information theory. This is called strong subjectivity. So HA times HB times HC times others. So let's take a system into 3 parts and maybe also other, so that there are no overlap. A, B, C, and there are no overlap at all. They compose this way. And once we did this, then always for any quantum system, any quantum mechanical system, this inequality is true. So SAB means A union B. So SAB plus SBC should be greater than SABC and SB. I think I already mentioned this in the context of holographic entanglement, and the holographic entanglement gives some geometrical proof of this in a few days before. But anyway, this is a strong subjectivity. This is called strong. This is very, very important, very, very fundamentally important in quantum information theory. And also this is kind of analogous to second law of thermodynamics. And indeed, we can show this is a kind of generalization of second law of thermodynamics, but because it can be derived from monotonicity of relative entropy. Strong subjectivity, SSA, follows from monotonicity of relative entropy. Relative entropy is defined by this. It's a measure the distance between two different density matrix, rho and sigma. This is not symmetric, but still very useful. And if rho and sigma is the same, this is just equals to 0. And this is always, we can show this is non-negative. It's always non-negative. So it looks like distance. And we can also show that this is very non-trivially, you can show monotonicity property. This is given by this. Or maybe, so, or more maybe like this. The rho sigma always greater than rho prime sigma prime. And rho prime sigma prime is actually coarse-graining of rho and sigma. Prime means coarse-grained. Maybe taking a trace, some partial trace, or some CBTP map or something like this. So some coarse-grained states is more difficult to distinguish. This inequality just says that, right? This fine-grained state is easier to distinguish. Distance is very enhanced. But if we trace out something, then distance gets shrinks and more difficult to distinguish. So and if we admit this, it's immediately clear that this strong subjectivity holds because we can show this. Right, this rho ABC and rho A times rho BC, just plug this in and we trace out C. Right, definitely this inequality true. So this is just rewrite this in terms of entropy, you just get this is just equivalent. These two are equivalent, trivially equivalent. So stronger subjectivity is sort of monotonicity of relative entropy or sort of second law of thermodynamics because this is a kind of free energy. Free energy is so at the thermodynamic equilibrium, so free energy becomes minimum. So the same statement. Okay, so idea to use this strong subjectivity to prove such a monotonicity property of quantum field theory like c-theorem and G-theorem. So to prove the c-theorem, it's not actually, it's surprisingly simple. So we rewrite this strong subjectivity like this way. This is the same thing, right? I mean, now A and B has some overlap region. But this A means this plus this, so that means that here it's AB, this AB, and BC. BC is a B. And there is an overlap, that namely this B. B is the overlap, right, between these two guys. And B is here, so overlap is here, and the union also here. These two are equivalent. So now we apply strong subjectivity to 1 plus 1 dimensional relativistic field theory. Relativistic invariance, Lorentz invariance is very, very important here. Without that, we cannot prove anything. So yeah, for that, so how we can choose A and B and C, A and B. So we choose this way. So it's a relativistic way. So this is a time and space, right? Two-dimensional space, and we choose A to be slightly tilted, Lorentz boosted. So because Lorentz symmetry, this is also a nice subsystem, right? So you can think this is a constant time by boosting time. And B also take this way. This is also fine. Naively, you think you want to take B and A like this way, right? But this is not necessarily because we can boost it. So we can boost this subsystem B. Then causality, relativistic causality, and says that. So this black line, these are okay. So this black guy. Right. Okay. So this black line is a null line, right line. It's light line. We choose that one. And let's take A and B as symmetric, the same length, just a G2 symmetry for simplicity. And then this guy, this small interval is actually regarded as A union B because any signal from A and B always pass through, both pass through A and B. But the green guy is larger interval. So signal from here is the intersect either A or B, right? Always. So that way, this looks like A union B. So, and geometrically very easy. So using just the usual Lorentzian geometry, you can easily see that the length, so invariant length of A times B is equal to invariant length of A union B and A union B and A cap B. You can very easy to prove this inequality by just putting some, for example, coordinates. And so now we take this length of A union B, the exponential X, and the intersection of A and B, the exponential Y. X is definitely larger than Y. Then A size of A and B looks like exponential X plus Y over 2 because of this relation, right? Because of this relation. And A and B are symmetric chosen. So then a strong subjectivity SA plus SB is greater than this guy is just written in terms of this, right? In terms of X and Y, so ASA is like this. This is something we know very much, right? This inequality we often see. This is really just says that function S is concave function. Second derivative is negative and non-positive. Okay? So it's like middle point is here, but it's this middle average of this guy is here. but this guy is like top here. It's much larger. So this actually says that immediately tells us entropic c-theorem, proof of c-theorem, because so for 2D CFT, we can have this, right? Because length is exponential x. So this means that c times x, right? And derivative of s is central charge at a fixed point. So and we just generalize central charge to non-conformal setup. So this is relativistic. I mean, field theory is not necessarily conformal invariant. It can have some mass gap, relevant perturbation, some conformal theory. So then derivative of x, it looks like central charge. It's called c function, and this means second derivative. That means derivative of c function. So we define c function this way, right? Then derivative of that is negative, non-positive. That means always decreasing, right? And RG flow. So this gives a nice entropic system. Okay. So now I'd like to generalize this to G-theorem, but maybe it's good time have a maybe short break now. So if you have any question, please also ask now. Okay, so let me continue. So I'd like to explain this main point of this talk. It's like a G-theorem. So G-theorem is a kind of boundary version of this theorem. The proof is, and indeed we want to derive this from the use of this strong subjectivity. Slightly proof is more complicated, but and then I would like to give an interpretation using ADS BCFT. Okay, so definition of this is a definition of G function. I already explained, introduced this G function in entanglement entropy, but historically, it's the first introduced by Affleck and Ludwig. This is definition is come from this disk amplitude. Basically, we calculate disk amplitude with some boundary condition alpha in the BCFT. So boundary conformal is preserved, and that case, partition function is G. And taking log of that, this is a boundary entropy. So G is a disk amplitude. And in terms of boundary state language, it's just overlap with vacuum state and the boundary state. These are just disk amplitude. This is disk. I mean, I should write this. The disk amplitude. Partition function, disk, on disk. Okay. So, and in other words, this is equivalent to the following one. This is a cylinder amplitude. So you take a cylinder with boundary condition alpha and beta. These are both are conformal invariant. And we take this computed by sandwiching some boundary state, two different boundary state, and with some propagator. Right? And this is a time evolution. You got this Euclidean time, exponential h. H is Hamiltonian, and Euclidean time is L. Right? And you can take L goes to large, then they factorize into this amplitude and just inside this long cylinder, only ground state propagates. Ground state is E0, energy is E0, ground state energy, and then it's just this amplitude, right? Factorize into this amplitude, G alpha, and you can extract G alpha conveniently more in this cylinder amplitude because we can normalize boundary state very well in this calculation. And third definition is the equivalent. Is 1, 2, 3 are equivalent. Third definition is the entanglement entropy, as we already mentioned. So we take a boundary, and there's a BCFT lives here, and there's a time direction, space direction, and we decompose space direction A and B like this. And this interval A, length of interval A is capital L. Then entanglement entropy for this region is like C/6 log 2 L over epsilon. You can put some mirror charge here. This looks like single interval entanglement, which is C/3, but take a square root, and that means C/6. But there is an extra piece. This is a boundary entropy, log G alpha. G is entropy, and log of G is an entropy, just as a convention. Entropy is a log of partial function. G is a partial function, and this is a G function. So these are UV fixed point, a conformal invariant fixed point. So G-theorem argues, this is Affleck-Ludwig's G-theorem argues the following. So G function monotonically decreasing under a boundary RG flow. Boundary RG flow means bulk we don't do. So bulk is already conformal invariant, critical point. And there is a boundary, right? And on localize, we assume some relevant perturbation localized on the boundary. This is boundary perturbation. We don't do anything in the bulk. Bulk is always conformal invariant, but we break boundary conformal invariance by putting some relevant perturbation. And G function in this context is originally just disk partition function. We just generalize this to non-conformal case, disk partition function. And actually, there is a several proof of this theorem. It's pretty done correctly, and by using field theoretic proof, and using also relative entropy, Cassini, Andrea, Trova proof, this theorem in some quantum information theoretical. But what I would like to give here is a more simpler one, just using strong subjectivity. So that, I mean, just generalization of entropic c-theorem, which I explained. So that's coming next. And the entanglement entropy into the BCFT and G function, this is already mentioned. And this setup, we always work with this setup. Subsystem is A is here, and the length is L, then we have this. And this we are interested in this constant piece. But now new thing here is like we now breaks boundary conformal invariance. We add some relevant perturbation, example here, mass term, or localize only as a boundary. Okay, and then bulk is always conformal invariance, but boundary breaks. And then it's not clear this we get this formula. Indeed, this log G function, this log G part depends on length L, not just constant. In the conformal invariant case, there are no only L dependencies only here, and G's are just constant, but now this G becomes L dependent in non-conformal boundary. So here it's no, we breaks conformal invariance, it's non-conformal. Conformal, but in the bulk is always conformal. And then when boundary breaks conformal invariance, though bulk is CFT, this boundary entropy depends on the size of it, as I mentioned here. And we'd like to show G log G or G monotonically decreases as a function where this is a G theorem. This is a G theorem, but this is a bit different from original G theorem, right? Just not talking about this computed, we call it the entropic G theorem. So all other proofs listed here are all for this disk partition function, okay? But here we only talk about the G theorem for entanglement entropy. But if we talk about fixed point, they are equivalent, right? Because the fixed point, this value, and this partition agree with each other. So if we just talk about infrared and the UV value, these are all the same, but the interpolating function is different. So we are using some entropic one. That's what I'd like to explain. But it's I'm sure that this what we're gonna talk about is much simpler than all of three approaches. So easy to understand relatively. So, but for that we need two tricks. I'd like to explain two different tricks, important points. So this is again the boosting because we are talking about this tilted like configuration. So if we think this subsystem A here, right? This is a setup we already talked about. So this green guy, this green guy is this one, this setup, right? But you can tilt it slightly. That's still the same entropy. SA prime is equal to SA. This is because this region, we can talk about mirror of this interval, this like this. And you can deform this interval to this guy, still same, right? This two are exactly the same subsystem in terms of Hilbert space. Because all information from here, it's always passed through A prime. And also other things through. Information A prime is always passed through A. So this is entanglement entropy for A and A prime is the same. That's the first point. So that's the reason. So we can also talk about A prime, but then we can regard this entropy as just length L in this L, real distance, not this distance. And the other thing, another trick is like we can talk about in general the tilted subsystem, and both are not at the end of the boundary, not at the boundary. So that, but still in general it's quite complicated, right? It's a 4 parameter. then, even if we have some strong subjectivity inequality, it's very difficult to simplify it. But there is a trick that we boost this interval to almost right-like. So if A gets closer to right-like, we can approximate this is a well-known formula, this log 3 over C formula. This is because in that limit, we have an infinite boost. So this looks like right-like. That means this length is very small. Invariant length is almost zero. Right? That means very UV interval. We can forget about the presence of boundary because this length is very shorter compared with this distance. So we can forget about this boundary and just use ground state usual entanglement entropy form. So these two are very crucial to derive strong subjectivity. To prove that, we have again this kind of tilted one, but slightly more tilted one, not symmetric one we choose. These black lines are right-like direction, null line. So we take this x and t and we choose this coordinate uu, and this is origin and ss, so obviously right-like. And we have another right-like line and take this one. And this point to 2s minus b and b and 2s minus w of tau. And anyway, the entropy for A is really one end point at the boundary, so it looks like this, right? This is, I'm using this one, this result. Even though it's tilted, you just read off the value of x coordinate. The x coordinate 2s minus b, it's like this. And you can also talk about A union B, A union B also, right? This x coordinate 2s minus b. This entropy called S, this somehow disconnected. Its meaning is clear in holographic picture later. We call it this. And this tilted guy is non-trivial, right? Naively. A union A cap B, and B is, there are two endpoints outside of boundary, so it depends on very complicated way. But now take these two limits so that this guy, right-like, this guy also right-like. Both are right-like. We take that limit. Then we can approximate, as I mentioned, just the usual ground state formula, and it can be simplified this way. And now we plug this. The strong subjectivity tells us that this combination is always positive, non-negative. So, and we can simplify SA, and so we just plug SA, like this formula and this formula here, and we simplify this guy like this way, and this guy to be this way, so we get this, and we take a difference, so we get this one. So now it looks very simple. Now we impose this is positive, right? No negative. We impose this is, we want to solve this condition. So then actually, so yeah, because we take this W, so we take a limit B and W are very close to each other. So they close to that means we can replace this with derivative, right? So then what we got is dSTL is bounded by C over 6, 1 over L minus S. But actually, we can take one more limit that S can be very, very small. Still, this is true. Then we get this form, this equality. This already proven holographic, G-theorem, entropic G-theorem. Because we can define, already we mentioned here, this part is a G function. We just subtract this guy, right? We take this difference, and we take derivative to show G-theorem, and indeed, this inequality tells us that obviously this is derivative, length derivative of G function is negative and non-positive. So that means as L, length scale goes to larger, then G function gets decreased. That means we go to infrared, this G function becomes small. So this is a holography, I'm not using any holography. This is a BCFT and quantum information theoretic proof of G-theorem. It's a quite a very simple geometrical form, geometrical argument. Okay, so, and we can generalize this argument to interface CFT, but maybe these are complicated. I'm not talking about just interface CFT, just the two BCFT attached to each other. But this two BCFT is not equivalent, not identical. There is some interface here. You can just double copy of this intervals, and you can prove also Now it's a double copy, so it's like C over 3 log L, but there is an extra piece. This is, and we can show this theorem also this set. Even if these two guys are different central charge, C1 and C2 still we can prove this. Okay, so now I go to holography. So yeah, what about strong subjectivity? So I already, I mean, in Monday I explained how to derive strong subjectivity in holographic entanglement. This is very simple. But what about ADS BCFT? Can we derive strong subjectivity? At least, actually, it turns out for static setup, if we talk about static background, derivation of strong subjectivity is almost same as usual entanglement, usual ADS CFT. So ADS BCFT, its strong subjectivity is same as ADS EFT. If we try to think about it, it's very easy to find. So I'm not going to talk about this. This is trivial. So static setup is nothing interesting, but if there is some Lorentzian time trivial time evolution is involved, then it's quite important. Or some boosting. Boosting also non-trivial time evolution appears. So to derive strong subjectivity in Lorentzian setup, we consider the following setup. So we have an extra dimension Z and X. Right. This looks like static because we have a time direction, and this is a subsystem. So this is a subsystem at t equals 0, and this is the end of the word, right? But actually, in the end, to understand this better, we need to boost. So then we need a really Lorentzian thing. We have to go beyond this kind of trivial picture, trivial situation. Anyway, so this is the end of the word brane, and everything is extended in the time direction, which is vertical to this seat. And the subsystem is here. The boundaries, BCFT lives here. CFT lives here. And this is the subsystem A. And the entanglement entropy for A is computed by this geodesic length, right? This geodesic length is this gamma P or gamma A is end on some point on the end of the word brane. So we just need to calculate this length, but also we have to minimize over choice of this P prime, right? We can take this guy is gamma A or this guy or gamma A, but we have to minimize, as I mentioned. This is about the island resolution. And so we calculated. So this is a bit complicated, but you can do it in using just the usual formula of geodesic length in ADS. So, and we can relate this location L and location A. A is the x coordinate of this P prime, because this is always part of arc, round circle. So once you specify this guy and this guy, you can precisely connect this 2 points by geodesic, but also you can require P prime gives a minimum value of gamma P. So that fixes everything. And so finally, we get this geodesic length standard of this one. The A is a function, this parameterized end of the word. G is some fixed function which parameterizes the location profile of end of the word, right? So, and we get this length. This is a holographic entanglement basically, and we take a derivative of L. Capital L is the size of subsystem. This is important to see this, right? G-theorem like this. And we take a derivative of L. That's what we do. Then in the end, we reach this simple formula, just derivative of profile. And this constraint profile of end of the word brane actually, because this should be positive, right? So this should be non-negative to require like this. We want to see this. So that actually to see this actually, so we can take derivative of this guy, and then you get the. So we take a dot at Z, and we take again derivative of A. Then this looks like A Z dot, and this A other term cancel. And this turned out to be negative because we usually impose null energy condition on the end of the work. But this null energy condition needs this time direction. Any static setup, we cannot derive this configuration. If we ignore time direction, we cannot derive this formula. This formula is derived because we are talking about Lorentzian time direction. So that means this is obviously this goes beyond this kind of static picture. And anyway, using this non-linear condition, you can prove that G-theorem is true. Yeah. So that this is actually holographic counterpart of G-theorem. But previously, I said that we proved this entropic G-theorem. This is much stronger. This is we don't need holography. That means we can go beyond. This kind of classical gravity dual calculation. It includes even quantum gravity. Okay, but anyway, so what this usual holography, what this G-theorem tells us. So this here is a geometrical consequence of G-theorem. So this is there is a is BCFT. So we have this is A is a BCFT, right? And the end of the word range is green curve. But the point is that, so what we find, G function is monotonically decreasing or also equivalently G prime prime, G prime prime is negative, non-positive. That means actually it bends this way. As a function of Z, it's like a concave function, so it should go this way, not go this way. This is very important, especially when we talk about two different subsystems. Maybe also I write it here. Let's take subsystem A, whether they can be connected, but it's not possible because it's always go this way, right? There are no way to connect it. To connect it, we need this kind of end of the word plane, right? Like this. But this violates G-theorem, this condition. The primary, in this case, is positive, but it's negative, should be negative. So that way, we cannot connect these two regions, and this means that we cannot have a traversable one-hole between A and B. I'm assuming this static configuration, but the A and B cannot be connected. So interestingly, G-theorem prohibits this kind of absence of traversal one-hole. And but moreover, as I mentioned, so this we prove now. So the entropic G-theorem, this is much more strong, and that because we don't need any classical gravity. So we expect something like this. No traversal one-hole is also true in quantum gravity limit. That's suggested that formula. And this is a more generally it is called topological censorship. So this means that we have topological censorship in the presence of boundary or end of the world. Okay. So these are holographic consequences, and I'm using some rest of time. I would like to switch to the other application of ADS BCFT. So this is but the idea is very simple. So we have an end of the word range, and we want to put scalar field. And we are going to mainly working in ADS3 BCFT2, but new thing is that we put some scalar field. And we just assume this very simple action. This is an action on the end of the word brane Q, given the Hawking term and the kinetic term of scalar and the scalar potential. This is our model. This simple model actually gives many interesting new results. And the boundary condition by taking a variation of HAB, you get this equation. So this is a familiar term, and this is a boundary energy stress tensor. But now in terms of scalar field, it takes this form, a potential and a kinetic term and so on. Okay. So we can actually analyze this gravity dual of this Barak renormalization group law. In the context of G-theorem, I already talk about boundary renormalization group law, but we can realize gravity dual of that because we're using this scalar field. This scalar field is very important. So, and in the presence of scalar field, I'm talking about the ADS3 case. The equation motion is summarized into two equations, like very simple equation, two equations. And here is one solution. So we are talking about this kind of setup. This is an extra dimension, and this is a BCFT lives in the lower half plane. And this is the end of the word range. So we calculate, anyway, this is a CFT lives here. And this is the end of the word range. As I mentioned, end of the word range bend towards the interior, right? It not go outside. So this is also in this case, it should be true because G prime prime is positive. Sorry, it's now we change the coordinates. Now it's G prime prime is positive to bend this way, concave function. But it's because phi dot square is positive. And this is a positive energy, right? Phi dot square should be always positive because of phi is a scalar field. But that means the kinetic term is regular and it's positive energy. And that's equivalent to Z prime prime is non-negative. So that's bend. So end of the other bend this way. As we expected, this should be true to have a G-theorem, as I explained. In this setup, so we can, for example, especially we choose this profile, G tau is like tau plus tau square. It's like tau square means like this. This obviously satisfied. This is positive. And if we have potential like this form, we get this kind of profile. So this is bending in the inside, right? And we can find, and we can calculate boundary entropy, and indeed it's monotonically decreasing as we expect. And moreover, so we can find some very exotic solution in the presence of scalar field. This is a more normal solution like this, but there is actually this kind of, torus, half torus. We have torus donuts, and we cut it into half. This kind of setup also realized only if we introduce scalar fields. Without scalar fields, this configuration actually we cannot find. This kind of non-trivial topology also appears. And finally, I'd like to talk about entanglement phase transition. So this is actually interesting application of ADS BCFT. So we consider ADS 3 BCFT 2. And as we mentioned, also we can talk about the cylinder, right? On cylinder, there are two boundaries. This is boundary number 1, and there's a boundary number 2. And what we want to do is to change boundary condition between these two by putting scalar field. So we have an ADS BCFT with two ends of the word domain, or one end of the word domain, but two boundaries. So we have a two boundary, and we put some scalar field on end of the word domain. So maybe one picture is like this. This is the Z direction, and there is a boundary. So this is a BCFT lives here. BCFT lives here. This boundary is this boundary, and the other boundary, this 1 and 2, second boundary is here. And end of the boundary may be connected or disconnected. There are two possibilities, and that is written here also. So disconnected situation, this connected situation. And so there is an interesting phase transition between them. That's an interesting thing. So anyway, we can put some scalar field on end of the word brain and the non-trivial profile. So scalar field values here it's phi 1, but it's different from phi 2. There is a kind of non-trivial gradient of scalar field. Maybe sometimes kink-like solution. So that boundary scalar field is phi 0 here and phi 0 plus delta phi. And so delta phi is very important. And here we assume potential is trivial and just massless scalar field. So the value of scalar field is not important. It's a moduli, but difference is very important. And different, if these two guys are different, that means these two boundaries have a different boundary condition. So we plotted the phase diagram. This is a horizontal axis is delta phi. How much boundary condition are different? And the vertical axis is temperature. Temperature is this kind of Euclidean time compactification level. The beta is the inverse temperature. This temperature. 1 over temperature. This is a conformal field series, so it's like ratio of this distance and this imaginary periodicity. Inverse time. Beta. Inverse temperature. Okay, so anyway, so this is a phase diagram. It looks like this. This is a very interesting point, and there is a 3 phase point, 3 different geometry involved. This region, when delta phi is small, it's a thermal radius. So that means end of the word range is connected. And this background geometry is thermal radius. So this is low temperature phase. This is something we know, right? At delta phi equals 0, we know this is a Hawking page transition, something called it's a thermal radius after low energy phase, low temperature phase, we have a thermal radius phase, and high temperature phase, we have a BTZ, like some black hole, radius black hole phase. But now we generalize this famous Hawking page transition in the presence of delta phi. And then transition temperature decreasing as delta phi gets larger. And interestingly, there's a critical point here appears. And delta phi at some very critical value, there is this border, it becomes goes to 0 temperature. And here, geometry becomes just Poincare radius. So but this inside the region looks like Poincare. And there, I think this is connected, but Poincare radius appears. And beyond that, even if temperature is 0, we need to choose this BTZ phase so that there is a horizon and there is a disconnected end of the vertebrae. So this is an interesting phase diagram, but also this phase diagram looks similar to QCD or other confining theory, because here this is a confined phase. This is, you might think this as a chemical potential or a baryon chemical potential. This is a temperature. Then high density, or this is density. High density, we have a deconfined phase. So indeed, we have a black hole phase. But new thing here, we have a critical point. That's how you can see in this picture. Okay. So, but so here is this geometrical picture. Same thing. As I thought, this is when delta phi is small, they are connected. But delta phi is very large, they are disconnected. But now, interesting thing is to take a double weak rotation. This is a final point of this my talk. So then we have this thermal radius becomes BTZ, like we exchange time and space, and this BTZ becomes thermal radius. But anyway, for BTZ phase, we have an end of the word brane and the Euclidean picture, because this is the same as this guy, just same as this guy. But at t equals 0, we continue to Lorentzian geometry. Then it goes to shrinks to 0 size like this way. There are non-trivial end of the vertebrae time evolution there. But in thermal radius case, it's localized here, right? End of the vertebrae. So after Lorentzian time evolution, just disappear. No end of the vertebrae at all. So then what about the calculation of entanglement? So here is a sketch. So after double weak rotation, and we want to compute this holographic entanglement, so that we take subsystem A to be this line, and we take this circumference to be infinite. This becomes beta goes to infinity. And beta is the inverse temperature, but here it's just space direction. Length of space direction, space compactification radius to be infinite. Then subsystem A, and then entanglement entropy is computed by connecting this endpoint to some point on the end of the vertebrae, just fixed by minimization, extremization. And then we see these two phases, BTZ phase, we can calculate entropy gamma A, and which is interestingly growing under time evolution. So linear T. So this is actually when delta phi equals 0, this point, this is actually same as a very famous example called Hartmann-Maldacena configuration. That is just starting from boundary state. This is a boundary state and just time evolved. So initially we have a completely disentangled direct product state, but under chaotic time evolution, entanglement entropy growing linearly. So this is exactly it. But as delta phi is introduced, this coefficient decreases. You can calculate this coefficient. And in the end, at the critical point, exactly this point, this coefficient goes to 0. And but nevertheless, this is a critical point. It looks like now linear T behavior changes into log T behavior in Poincare radius. And if we go beyond this critical point, it becomes trivial because no end of the vertebrae like this. just disappear, just stand same as the usual result. It's just constant, no time evolution at all. So that way, entanglement entropy, its time evolution behavior completely changes. It has this sort of transition, phase transition. But how, and this phase transition is very similar to this, what people call entanglement phase transition. This is a condensed matter literature. It's a kind of very hot topic these days. But originally, entanglement phase transition appeared this way. So we start with some chaotic time evolution, some Hamiltonian. But on top of usual Hamiltonian evolution, we put some projection measurement as some periodically. Then if we do projection measurement, then that reduces the entanglement entropy, obviously. It's a projection measurement that somehow induces dissipation or decoherence. That reduce the amount of entanglement. So without projection, as I mentioned, like here, so it's growing linearly because it's a chaotic time evolution. And initially, let's assume very small amount of entanglement, and the chaotic time evolution, entanglement growing linearly. But if we put some also projection each time at some probability, P is the probability of this projection, the amount of projection, less than some critical value, it's still linear T growth. But projection measurement induced at some particular ratio, critical ratio, it becomes logarithmic. And more than that, if we put a lot of projection, it just becomes finite. This behaves exactly the same as this behavior. This is quite interesting analogy. So in the ADS-CFT viewpoint, maybe so we start with some product states, and we have a Euclidean end of the world brane, and we have a non-trivial dynamics. And indeed, interestingly, the scalar field here actually turned out to be imaginary value for Lorentzian time evolution. It looks similar to this introducing this dissipating dynamics like projection. But at the same time, we have to be careful that this setup is not exactly the same as what people think, condensed matter people discussing as a measurement in phase transition, because we are talking about this kind of generalized state. So because we are talking about two different boundary conditions, so this boundary state is given by this as a scalar field value of phi 0, but this is, at the other boundary, we have a different boundary state with scalar fields of phi 0 plus delta phi. And this is no longer usual density matrix. Actually, it's not Hermitian. So in that sense, more properly, what we find is entanglement phase transition called pseudo-entropy. Pseudo-entropy I mentioned also in the Monday lecture, and I will give more details of pseudo-entropy, some other application of pseudo-entropy on next Monday, my final lecture. I will give more details, so I'm not going to detail, but anyway, this is not Hermitian density matrix. That means we are computing pseudo-entropy. And for pseudo-entropy, so still we can calculate its value as a minimal area or extremal surface area. So this prediction works. This calculation gamma A, this value is trustable. And we find this phase transition of pseudo-entropy. Okay. So I think, yeah, basically that's all for my lecture. So let me summarize. Strong subjectivity provides a new geometrical proof of G-theorem, as I mentioned, under RG flow, boundary RG flow. And in the holographic analysis of ADS BCFT, strong subjectivity is automatically satisfied in static background. But in Lorentzian boosted setup of ADS BCFT, strong subjectivity is satisfied if the null energy condition is imposed on the end of the world. And we constructed the class of expressed gravity duals of boundary RG flow by adding scalar field localized on end of the world. Okay, and when two boundary conditions are different in BCFT on a cylinder, its gravity dual predicts entanglement phase transition. I just in the end I mentioned. So like here are some small number of future directions. What about higher dimensional generalization of this ADS BCFT is not so much explored. Also, what about higher dimensional c-theorem and G-theorem? For c-theorem, up to 4 dimensions is known. G-theorem is not known higher than 2. Like 3-dimensional G-theorem might be quite interesting. And the strong subjectivity, you use the static space-time, but what about a static setup, but what about time-dependent situation? Does it tell some non-trivial constraints? And also recently there are interesting developmental algebraic approach to quantum field theory. Maybe can we have something to say or see on this theory? Okay, so basically these are all. Oh, thank you very much.